Okay, this is the version 1 of the Spring 17 Physics 1402 exam. The first question asks, an electron has a charge of negative E and a mass of m sub e. A proton has a charge of positive E and a mass of 1840 times the mass of the electron. So therefore a proton volt is equal to 1 electron volt. Why? Well, because the electron volt is the amount of energy that it takes to accelerate 1 electron through 1 volt potential difference. So the change of potential energy is equal to Q delta V. If Q is E and delta V is 1 volt, then this is equal to 1 electron volt. For a proton, this energy is just equal to, for an electron that would be negative E. So it would be negative 1 electron volt. But it depends on the sign of the potential difference because we're really just looking at the absolute value. So for a proton, it's just Q delta V again, and so this would be plus 1 eV. But that's not what the question's asking for. The question is just asking for how much energy is in an electron volt versus a proton volt. So positive energy could be that you're decreasing the kinetic and converting that into potential, or vice versa for negative. So in this case, it has nothing to do with mass, though. That's the important thing. So all of these options have to be wrong. It only has to do with the charge. So it would be 1 eV. Obviously, a proton volt is not used regularly. This is just a hypothetical kind of thing. So here you have on question 2 a charge with, it's a negative charge, and it's moving from here to point P of some certain distance in a region where you have the electric field directed upward as shown. What is the change in electric potential energy of the charge? That's 0. There's no change because there's no work done by the electric field. We're moving perpendicular to the field. If you remember that the electric potential energy, saw above, is equal to Q delta V, all right, and delta V is defined as negative E dot ds. Well, E dot ds, these two things are perpendicular to each other, so the potential difference is 0. Another way you can look at it is the work from non-conservative forces, which in this case work is from the electric force, is equal to the negative change in potential energy. And the definition of work is the integral of F dot ds. Well, this is the electric field doing the work, so that the force then is equal to QE. So this is equal to QE dot ds. And where'd the negative go? Because that's negative is still over here with the potential energy. So I can say the potential energy is equal to negative Q E dot ds, which is exactly what we have up here, right? Once you plug this in for the potential. So this again is 0. The next question asks, all right, so we've got these equipotential surfaces, various points on the equipotential surface near the conductor. 2 conductors here and here are labeled. This is obviously the positive, and this is must be the negatively charged conductor because the potential is higher over here. So how much work from a non-conservative outside force is required to move a negative 1 microcoulomb charge from A to E? From A to E. So it's a negative coulomb, a negative charge, and the negative charge should be moving this way. The electric force is in this direction, but the displacement is in the opposite direction. So that is why it's a non-conservative outside force that has to be moving this. So we can say that the work done by the non-conservative force there must be equal to the work from the conservative force, the negative work due to the conservative force. And that is because the work, it should say minimum probably, because he could do extra work and have some velocity at the end. But the minimum work must be exactly the opposite of the work that the electric field is doing, because the electric field is going to be doing negative work as you move in opposite to where the force is. So we can find what the work from the electric field is and find the negative of that. So that is just going to be negative Fe dot ds, right? Which is negative Q E dot ds. Okay, so this work now is equal to Q delta V, because this, remember, delta V is defined as negative E dot ds. And so that is just going to be a, let's see, it's a negative 1.0 microcoulombs times delta V, which is final minus initial. So negative 30 minus 30, so that's negative 60 volt potential difference. So it equals a positive 60 times 10 to the negative 6. That comes from the micro there, the microcoulombs, joules. Wait a minute. Okay, this is actually a 70. I'm sorry. Goes from 30 to negative 40, so that's 70 volts, and this is 70 times 10 to the negative 6. Sorry, or plus 7.0 times 10 to the negative 5th joules. Positive. Okay. So the capacitance of a parallel plate capacitor can be increased by, well, remember this is equal to epsilon naught A over D. So if you increase the charge, well, that's not going to do anything. If you decrease the charge, that's not going to do anything, because we don't know what's happening to the voltage here. We do know capacitance is equal to charge per unit voltage, but you know, we're not changing the capacitance of the capacitor, because you could just increase the charge and increase the voltage at the same time. So if you increase the plate separation, so C is proportional to 1 over D, so that can't be true, because that would make it go down. But if you decrease the plate separation, this gets smaller, this gets larger. And of course, decreasing the plate area decreases the capacitance. So the junction rule, which is true of the currents? Well, if you remember, the junction rule tells us that the current flowing in, I0, must equal the current flowing out, I1 plus I2. That's not one of our options, but I can scratch that out because that's not true. What if I1, I0 minus I2? That's true. That's not true, obviously. And I2 would equal I1, I0 minus I1. That's not true. So, and of course, found that in the beginning. So the answer is D. So a student says that the second two light bulbs in series is dimmer than the other one because the first one uses up some of the current. That is not true. Is same throughout series. Now the voltage drops, so the energy per electron is dropping as you go across one resistor, as it's bouncing around in the resistor, and then it drops again going through the second one. So the energy per electron does drop, but the current stays the same. So here we have several point charges. If you move a particle of charge plus q from point A to point D, identify the following quantities as positive, 0, or negative. Well, A to point D, okay, so the distance between A and this charge is the same as the distance between D and that charge, and the distance between A and the charge over here is the same as the distance between this and that charge. So you're basically just flipping things around. There's no change in potential energy. Okay. And that's because the charges are the same. So in other words, if we wanted to look at it, so change in electric potential energy is equal to Q delta V, which is equal to Q times KQ over D. That's the distance to the first one. Plus KQ over 4D, because it's 1, 2, 3, 4D away from the other charge. And once you move this over here, you have the same situation. It's the same potential potential. So B, as the work done by the net electric force on the particle as you move, that's the net force due to the other two particles. Well, if the potential difference is the same, work is equal to the negative change in work conservative is equal to the negative change in potential. So we found that was 0, so this must be 0 too. What is the work done by your force? Well, our work is going to be the negative of the work of the conservative force, so that is 0. Because we moved it and we brought it to rest, so there's no kinetic energy. So our work must be equal to the work of the conservative force, so that's 0. So what are the answers if you instead, the positive particle moved from B to C? It's the same in every one of them. Because here you are 1D away from one charge, 2D away from the other charge. When you move to C, you're 2D away from that charge, 1D away from that charge. So in the figure below, a particle is to be released from rest at point A and then is to be accelerated directly through point B by an electric field. The potential difference between A and B is 100 volts, which should be the higher electric potential if the particle is an electron. So electron must move towards lower, electron's going to move towards points of higher potential difference. So B must be higher. We asked for an electron, yeah. So VB is greater than VA. Remember, the electric field must go this way if an electron is moving from A to B. For part B, what if it's a proton? Well, if it's moving from A to B by the electric force, in that case, the electric field must be this way, so A is the higher potential. VA is higher than VB. The electron moves to areas of greater potential. Proton moves to areas of lower potential. And C, an alpha particle that's got 2 protons and 2 neutrons, so that's a positively charged particle. So again, it's A, where VA is greater than VB. Now, part D says rank the kinetic energies of the particles at point B greatest first. Well, remember that the kinetic energy is going to equal the change of kinetic energy, change in K, not KE, is going to equal the change in potential energy, because the change in potential is being converted into kinetic. Well, for B and A, so Ka equals Kb, the reason why is because you've got the same charge. So this is equal to Q delta V. If the charge is the same and the potential difference is the same, then the potential energy is the same, which means the kinetic is the same. However, that's going to be less than the kinetic energy from the alpha particle, because the alpha particle has higher charge. So it has twice the charge. So it's going to be twice as much kinetic energy as A and B have. Okay, so this question, you've got a uniform electric field directed in the negative y direction. You have the coordinates of the 2 points. Calculate the electric potential difference, VB minus VA, experienced by a hypothetical particle moved along the dashed path. Well, if I call this path 1 and path 2, I can say the total change in potential difference is equal to the change in potential difference from path 1 plus the change in potential difference from path 2. Now, given the definition of potential difference, I can write ds, I'll call it ds1 because it's along path 1, minus the integral of E dot ds2. So I hope you see already that this must equal 0 because the dot product between E and ds is 0. So remember, dot product of two vectors that are perpendicular is 0. The electric field is down, the displacement in part 2 is across. So the change in potential is just equal to negative E dot ds1. E is a constant, so I can pull it out of the integral. I can just integrate along 1 by, I have the coordinates, so I can find that. So that's negative E dot S1. I integrated that. Now this is equal to negative E S1 cosine of theta, where theta is 180. Because the electric field is down and the displacement is up. So that cosine of 180 becomes a negative 1, so the change in voltage is plus ES1, which is just, 325 volts per meter times the displacement in the y direction only. So we're looking at A to the y coordinate of B, so this would be half a meter minus a negative, so that's plus 0.300 meters. So delta V, that's 325 times, what did I say, too many zeros, times 0.8, which is 260 volts. Part B, let's calculate the electric potential difference from B to A using a straight line path going in that direction. Okay, well, we could just use an argument about path independence and say it's going to be 260 volts, but let's work it out and see what it is. We know it's going to come to the same answer, but let's just prove it. I'll call it S3. And so the electric field is constant, so I can factor that out of the integral, so I have just E dot S3, which is just equal to, we could do it ES3 cosine of theta, Or I could put it in unit vector notation, and E in that case is just equal to negative 325 volts per meter J hat, and S3 is equal to, let's see, we know we're moving 0.8 in the y direction, so in the x direction we are moving from negative 0.2 to positive 0.4, so that's plus 0.6 meters I hat plus 0.800 meters J hat. So I'm going to go back and do the dot product in unit vector notation. That will be negative EX times S3X plus EY times S3Y, or it equals, and remember this is equal to 0 because EX is equal to 0. So this is equal to negative 325 volts per meter times 0.800 meters. What do you know? That's going to come out to exactly what we have up here because the negatives will cancel out, and that'll be plus 260 volts. You get the same thing. Or you could have also just used trigonometry. E points downward, S3 points upward. We need to find this angle between them, and we can use the formula negative ESX cosine theta. And when you find that angle theta, that's going to give you, that's an angle greater than 90, so cosine of that is going to give you a negative, and that's going to come out to be positive. But to do this, we would have to find the magnitude of S3, which means we would have to do Pythagorean theorem. Okay, so the next one, we have a 2 nanofarad capacitor with some initial charge, and it's discharged through a resistor. I'm going to draw it up here. What is the maximum current in the resistor? Well, if this had been charging and we had hooked it up to a battery, it's asked what's the maximum charge, that wouldn't be too difficult because we would just I equals V over R. But in this case, we don't have the battery. But if we had the voltage over the capacitor, we could use I equals V over R and find it that way. We don't have that either. So let's instead look at, in order to find the maximum current, let's look at the charge for a discharging capacitor is equal to that. It's just the equation we know. So what is the current? Well, the current is equal to the derivative with respect to time of charge, which is equal to Q max, negative Q max over RC. When I differentiate this, I get negative 1 over RC. That comes down e to the negative t over RC. So I equals I max when t equals 0. So at that point, I equals negative Q max over RC e to the 0th. That's just equal to 1. So your I max is that right there. Negative Q over RC. If I plug in, I can get negative 5.10 microcoulombs over 1.30 kiloohms times 2.00 nanofarads. This is I max. That equals, what is it, 1.96 amps. So the next question asks us to calculate the current in the resistor 9 microseconds after the resistor is connected across the terminals of the battery. So I of 9 seconds is just equal to our I max, e to the negative t over RC. which is just 1.96 amps, times E equals negative T over RC. You can plug in the numbers for that. So I of 9, and this is 9 microseconds, excuse me. Negative 61.5 milliamps. Part C, what charge remains on the capacitor after 8 microseconds? Well, that's not too bad because we just go back to our equation for charge. And so now we can just plug in 5.10 microcoulombs times e to the negative, what was it, 8? E to the negative 8.00 microseconds over RC. So Q then is equal to 0.235 microcoulombs. So we now have a circuit, a combination circuit, and we want to find the power delivered to each resistor in the circuit shown. Okay, so in order to find the power in each current, we must find the current through each circuit, or voltage drop across. That would work too. So first thing, let's reduce all these down. So I can say, I can draw this circuit. I'll call this R2, R31, R4. And we know R31 is equal to 1 over 3 ohms plus 1 over 1 ohms. Again, 1, so that's 1/3 plus 1, so that's 4/3. So R31 equals 3/4 ohms. Okay. Well, I can't find the voltage drop across that because I don't know what the current through is. So in order to find the current, I'm going to have to combine all of these into one equivalent resistor. Cut R1, 2, 3, 4. And R1, 2, 3, 4 is just 2 ohms. Well, I'll write that symbolically. R1 plus R2 plus R2 plus R31 plus R4. So I'm adding this, 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 and this. So R1, 2, 3, 4 is equal to 6.75 ohms. So that means the current 1 through 4 is equal to V1 through 4 over R1 through 4, which is 18 volts over 6.75 ohms. I1 through 4 is equal to, do I have this somewhere? 2.67 amps. So then we know that's the current through R2 and R4, so we can immediately find the power through R2, because that's just I2 squared R2, or I1 through 4 R2, because remember the current through the whole circuit is the same as the current through each resistor in series, so that's 2.67 amps squared times 2 ohms. So power in 2 is equal to 1.34. Now the power through that first resistor is 14.3 watts. And we can also find the power through this one too. The power in the resistor 4 is I4 R4 I squared, which is I1 through 4 squared R4, which is just equal to 2.67 amps squared times 4 ohms, or 28.5 watts. Okay, so now we haven't done anything about these two things in parallel, but we can find the current through each one of these branches if we find the voltage drop across, across the equivalent resistor. So the voltage drop across 3.1 is equal to the current through 3.1 times the resistance of 3.1. The current through that equivalent resistor is the same as the current through the whole circuit. So that's just I1 through 4 R31, or 2.67 amps times 3/4 ohms. So 2.67 times 3 divided by 4. So V31 equals 2 volts, and that equals V3, and that equals V1, because it's the same voltage drop across here as it is across here. Now at this point we could find the currents, or we could just plug directly into the other power equation where P equals IV. No, we can't do that because we don't have the current, but I can substitute in and find V3 squared over R3. So I know these things now because this is just 2 volts divided by 3 ohms, so that's 4 divided by 3. So this power is about 1.34 watts. And you can do the same thing for 4. V4 squared over R4 is equal to, again, 2.00 volts because the voltage is the same, over 4 ohms. So P4 is equal to 1 watt. Oh, I'm sorry. I already did P4. I meant to say that's P1. I numbered it differently than I have before. So this is the power through that 1 ohm resistor, which means this is 1 and this is 4 watts. So this problem is especially tough. You're trying to find the current between A and E. It's a tough problem, and so the way so I've given you all these hints to kind of guide you in the right direction. If you can find the voltage drop across the 3 ohm resistor, then you can, or the 3R resistor, call it V3. Then you can find the current flowing through it, and you can find the current flowing out of E, so you can use those two together to find the current through A and E. So let's just redraw the circuit such that looks something like this, which is essentially the same circuit. All I did is bring A and E together, which you can do because they're connected together. So let's find R, 2R, 3R, 4R, E1, E2. Oh, I'm sorry, this is not just E1, E2, it's 2E. And I'll call this just E. I'm going to define I2 in this direction. And I3 is down. So let's look at, and if I do this, then I can define create another circuit like this, right? I can just combine those two resistors. So this is R, 2R, and this is, I'll just call it REQ, right? So REQ is equal to 1 over 3 ohms, 1 over 3 R's, not 3 ohms, plus 1 over 4R reciprocal. So this is what, 4, so that's 7/12, so that equals 12 over 7R. So can I find all these voltages? So it's I1, I2, I3. Well, you know that let's just take a loop. Let's say loop 1 is around this direction. So as you move through, you add E minus RI1 minus REQ I3 brings you to 0. So you've got I1 and I3. Now in the next loop, we'll go around, and let's say we start at this corner. So that's loop 2. So that's 2E. Now we're going against the chosen flow of I3, so we're going to add REQ I3. And again, we're going, oh, I'm sorry, wait a minute. If we're going this direction, let's go the other direction. Because we chose I2 to be in that direction, and we chose I3 to be in that direction. So let's just make things simpler. Do it that way. So I'm going to start here. Actually, I'll start on the other side of the battery. Move across the battery. So that's going to be 2E. The other way I chose it should have been minus 2E, but in this is the correct way, so we're doing plus 2E. Minus 2R I2 minus R equivalent I3 equals 0. So I'm going to give these equations numbers. I'll call this 2 and this 1. Why to go 2 and 1? Well, I'm just trying to match the key that I put online, so it's not out of order. And over here, the third equation that we're going to deal with is the junction rule that says I3 must equal the sum of I1 and I2 that come into that junction. I will call that equation 3. So what do we do? Well, if I look at equation 2, so we have equation I1, I2, and I3 in these two equations. So now that I have my three equations defined, I'm going to eliminate one of these variables from these two equations. I have I3 in both, so I can't deal with that, but I have I1 and I2. I can use equation 3 to eliminate one of them. Let's try eliminating I1. So I1 is I3 minus I2, and so I'll take equation 3 into equation 2. So E minus R times I3 minus I2 minus REQ I3 equals 0. So I can reorder this, group the I3 terms together. So minus RI3 minus REQ I3, so that's minus R plus REQ I3 minus, well, that's plus R I2. So this is still equation 2. I'll go back to equation 1. 2E minus 2 RI2 minus REQ I3 equals 0. Well, this is convenient. I don't have to do anything. Oh, yeah, I do. I mean, I have to multiply everything here by 2. So I'm just going to insert it in. Okay, so now I can add these two together. I have plus 2RI2 minus 2RI2. Add. So 2E plus 2E is 4E minus 2R plus REQ I3 minus REQ I3, and these two cancel out, so that equals 0. Okay, so I can now solve for I3. I'm going to have to group these a little bit. So it's minus 2 REQ I3 minus, so this is 4E minus 2R let's say plus, and put these in parentheses, minus 2R minus 3REQ I3. So I3 equals negative 4E over 2R plus 3REQ. That equals negative 4 let's see, what is the 250 volts over 2 times 1 kilo ohms plus 3 times 12/7 times 1 kilo ohm. Okay, I missed a negative. When I move this over, that should be negative. So I3 is 140 milliamps. Okay, so where do we go? We get a new sheet of paper. So now that we have I3, we could go back and find I2, right? So I3 into equation 1. So 2E minus 2R I2, which we now have, equal minus REQ I3 equals 0. So solve for I2. I2 equals 2E minus REQ I3 over 2R. So that equals 2 times 250 volts minus 12/7 times 1000 ohms times so that is going to be I2 then is equal to 130 milliamps. Okay, so we've got I2 and I3. If we look back at our situation here, I3 so we can find the voltage drop across REQ, which is just I3 times REQ. So that is 140 milliamps times 12 sevenths times 1,000 ohms. So 0.14 times 1,000 times 12 divided by 7. So that equals 240 volts. So now that we have REQ, we know that's the voltage drop across the 3 ohm resistor, so I can find I across the, what do we call that, 3 ohm, or I'll call it I4, is what crosses the 3 ohm resistor. So that is V3 over R3, if you want to say, 3R, excuse me. So that's 240 volts over 3,000 ohms. I4 equals 80 milliamps, excuse me. Okay, so now we've got the current. Now we know what the current is through this 3R resistor. So this is I4. We already know this because that is I2. So we'll call this I5, and I could just guess that it's in this direction. So I5 plus I4 equals I2 that flows out. So what we're looking for is I5. So I5 equals I2 minus I4, or I2, which we found up here, 130 milliamps minus 80 milliamps. I5 then is equal to 50 milliamps